Hey guys, in this video we're going to be talking about how to interpret tables and graphs of exponential functions. So let's get started. All right, the table to the right, we are going to use the table to the right to find the key features of an exponential function. All right, so first of all, we want to know what is the starting value of the function. Now remember, the starting value is always that number that's in front of the parentheses of an exponential function. So for example, y equals a times b to the x. This a value here is the starting value, and we get that value from when x is 0. Just like you do anytime you are using a quadratic or a linear function here, it is the y-intercept essentially. So all you have to do is find that in a table or on a graph. So here's where x is 0. That means my starting value is 18, okay? Common factor that the function is changing by. So in order to find that, what we need to do is figure out what are we multiplying by each time we go down this table. And there's actually a very, very simple way to do this. We already know that this table is exponential because I'm telling you that it is. So you don't have to try and figure out whether or not it's linear, quadratic, or exponential. I know that I'm going to multiply by 18 by something to get to 14.4. So all I'm going to do is do the opposite of multiplication to figure out what that number is. Now the opposite of multiplication is division. So I'm going to take the second number and divide it by the first. So 14.4 divided by 18 is 0.8. So that means to go from 18 to 14.4, we multiplied by 0.8. And we can always verify this by multiplying by, this is 0.8. Multiplying that number by 0.8 to see if we get it again. So multiply by 0.8, 0.8. So 14.4 times 0.8 is 11.52. And then we can try it again, and it just keeps working. So all I need to do is take the second number and divide it by the first to find the common factor, which in this case is 0.8. All right? And then is this growth or decay? Well, the number is less than 1, so therefore this is decay. And we know that because 0.8 is less than 1. And I think this pen is done for, so we're going to not use that one. All right, let's try another. That's it. All right, starting value of the function for this one. Again, they're telling us it is exponential. All we have to do is find all the answers. All right, so the starting value of the function is whatever y is when x is 0, so that's going to be 5. All right, what is the common factor that the function is changing by? I'm going to do 7 divided by 5. So 7 divided by 5 is 1.4. So we're going to put 1.4 right here. And then lastly, is this growth or decay? Well, 1.4 is greater than 1, so this is going to be growth because 1.4 is greater than 1. That's it. Let's try another. All right. The table to the right represents the amount of money in a bank account over the course of several years. Use the table to find the following key features of an exponential function. All right, same idea here. What is the starting value? It's whatever y is when x is 0, and you can assume that x is on the left, y is on the right. So that means the starting value of the account is $1,200. What is the common factor that the balance is changing by, and what does this mean in the context of the problem? All right, same idea. We're going to take 1290 and divide by 1200. So 1290 divided by 1200 is 1.075. Okay, so we're just going to draw an arrow here. So it's 1.075, which means that the account, first of all, it's increasing because this is bigger than 1. So increases by, and remember, you have to figure out what that percent is. So since this is bigger than 1, the number inside the equation that we could write, by the way, is going to be 1 plus whatever that number is. So I'm going to take 1 away to get the percent. So 1.075 minus 1 is 0.075, which is 7.5%. So 7.5% each year. Okay? And then part 3, this is growth. Because 1.075 is greater than 1. Let's actually go ahead and practice writing the equation. So if I have a starting value of 1200 and this is my common factor, that means that my equation is just y equals 1200 times 1.075 to the x. That's it. That would be the equation. Let's go back to the last one and write the equation for this one. Okay, so the equation is y equals, the starting value was 18, times the common factor is 0.8 to the x. And that would be it. That's the equation. All right, let's try another one. All right, the table to the right represents the value of a car over the course of several years. Use the table to find, again, the key features of the exponential function. All right, so first of all, what is the starting value of the car? The y-intercept is $26,500, so that is the starting value, $26,500. All right, what is the common factor that the balance is changing by? So I'm going to take 18,550 and divide by 26,500, and that's 0.7. I'm going to draw a little arrow over here, so that's 0.7, which means that the value of the car it's decreasing because this is less than 1, decreases by, and then we have to find the percent. So remember, it's 1 minus 0.7, because it would have been 1 minus a decimal to get to 0.7. So we have to figure out what that difference is. So it's 0.3, which is the same as 30% each year. Okay? All right, so then number 3, this is decay, because 0.7 is less than 1. So then if I went to write the equation, it would be y equals the starting value of 26,500 times the common factor of 0.7 to the x, or the number of years that have passed. And that would be it. All right, let's move on to some graphs. All right, it says use the graph to the right to find the following key features of an exponential function. Now, from a graph, I'm not generally going to ask you what the common factor is or how to write the equation, so you don't have to worry about that. The only thing that I'm asking you to find right now is what the starting value is and whether or not it is growth or decay, okay? So, first of all, the starting value is always the y-intercept. So I'm just gonna go to the graph and I'm gonna find the y-intercept, which is 100, okay? That's the starting value. Now, growth or decay, just like when you look at a linear function to see if it's going up from left to right or down from left to right, you look at the exponential function in the same way. So as I go to the right, the values or the y values are increasing. So this is going to be growth. And it's simply because as x increases, y also increases. Okay, let's try another. All right, what is the starting value? Once again, that's the y-intercept, which in this case is 50. Now this one, as I go to the right on x, as x is increasing, my y's are coming down. So this is decay. As x increases, y decreases. Simple as that. All right, on to the next one. The graph to the right shows the number of cases of the common cold that a hospital saw over time this winter. Use the graph to find the following key features. Okay, so what is the starting value of the function? It is right here at 10, which means when they first started keeping track of the number of cases of the common cold, it was 10 cases. Okay, so that's right at the beginning. And then as time goes on, as X increases, the number of cases of the cold also increased. So this is growth. As X increases, Y also increases. Very, very simple. All right, we got one more. The graph to the right represents the number of players entered into a tennis tournament. Use the graph to find the following key features of the exponential function. So once again, what was the starting value? That's right here at 8. That means at the beginning of the tournament, there were 8 players that were participating in the tournament. And then is this growth or decay, and how do you know? Once again, as time goes on, or as the number of matches increase, the number of players remaining decreases. So this is decay. As X increases, Y decreases, which makes sense. As the tournament goes on, there are less players remaining in the tournament because they ended up losing their match. But that's it. That's how you interpret exponential functions using their tables or their graphs.